Okay, a diving board is attached to a pool deck as shown in the diagram below. There it is. The diving board has a mass of 10 kilograms. What is the direction and size of the force in each support when a 60 kilogram person is standing on the edge? So here we're just doing one where the supports are both inside or closer to the object, but we're still looking for two unknown forces. I'm going to call this force A and I'm going to call this force B just to keep them separate. And to find B, I'm going to do the torques about A so that I eliminate A. So the torque about A is going to be equal to the radius of A times the force of A plus the radius of the board, so I'll call it the diving board, times the force of the diving board, plus the radius of the person times the force of the person, and the radius of force B times the force in B. Now the radius here for this one is 0, so that's how I get rid of that term, which is nice. And for this diving board not to flip over or break, we need the torque to add to 0. So the diving board here has a total length of 2.5, and we want to put its central location halfway through that, so 1.25 meters. So 1.25 meters from A, and it's a force of gravity acting on a 10 kilogram object. Let's give ourselves a little more space here. Plus the person is 2.5 meters from the end. They're also dealing with their force of gravity, negative 9.8 newtons per kilogram, and they have a mass of 60 kilograms. And finally, the radius of B is 1 meter away, and we don't know the force in B, so we'll just leave it like that. And we get a big equation that we can solve. Now I'm just going to go one quick step here and add all of these like terms. So I get, for this and this, negative 1,592.5 Newton meters. And so I can see that FB is equal to 1,592.5 Newton meters. So this is pushing up with this huge force. Now to get the force at A, I can do it a couple different ways. I can do the sum of the forces, or I can do the torque about B. I think I'll just do the sum of the forces this time. F net in the y direction has to add to 0, and that's going to be the force of gravity on the person, plus the force of gravity on the diving board, plus FB, plus the unknown FA. So the force of gravity on the person, the person is 60 times 9.8. Force of diving board, negative 9.8 kilograms or newtons per kilogram times the 10 kilogram mass plus the force of B, 1,592.5 newtons. Shouldn't be Newton meters anymore, it should just be newtons when you divide out the meters. And the force of B, or force of A. So this is 588, and this is negative 98, and this is 1,592.5 newtons, 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 and we're just missing the force in A. And I'm going to get 906.5 newtons. Negative. So to balance the torques here, this has to actually push way up, and then this has to push down. It makes sense that this has to pull down, because if this guy's out here trying to rotate the system this way, force of A must actually act down to keep the board from rotating. This is interesting. You see this if you go into people's backyard swimming pools and you see that their diving board is broken. It's often broken in one of two places. It's either snapped here due to the large forces experienced at point B, or this back part has ripped off of the ground because it wasn't able to provide enough downward force to keep the board from rotating into the pool if somebody too heavy was out there. So that's how you can find the forces acting on a diving board, or how you can find two unknown forces when you have someone that is standing outside the pivot point or outside one of the two forces. The forces end up going sort of in funny directions, which is kind of interesting.